All right, so welcome back. Before I get started, there was two things I wanted to mention from the outside world. So one is you might have heard that more than 600 people died from heat exhaustion at the Hajj in Saudi Arabia over the weekend. The temperature went up over 125 degrees Fahrenheit. And actually, there's still about 600 more people are missing. They don't know if they're dead or if they're in hospitals, different places. And I think this is like an example of the importance of our community to solve the climate problem. It's always been hot in Saudi Arabia in the summer, but 125 is unprecedented to get that hot. And you guys might feel it's hot here in Princeton, but actually it's usually pretty hot in Princeton in the summer. So maybe this is slightly hotter than usual. But 125 is ridiculous. And that kind of stuff is going to be happening more and more frequently until we solve the climate problem. So that's like a big thing on us. That might be kind of a downer news. I also have kind of positive news, I think, is that yesterday was a national holiday in the United States, a relatively new one called Juneteenth. And that holiday celebrates the end of slavery, which was a big part of this country for a couple hundred years. Well, even before it was a country, it was a colony. It was a lot of slavery, and even first 80 years that this is an independent country. Slavery was a big part of our country. And I would say that the fact that we could actually end that practice, even though a lot of people made a lot of money from slavery, but still was able to get a majority to oppose it. And then the fact that we could have a national holiday to celebrate that we accomplished that. I think it's just an example that people can actually accomplish things. I would say in my lifetime, things like the Paris Agreement are another example that you look at all the countries of the world, they're at each other's throats, they're always complaining about each other, and yet they're able to see the common human interest in trying to solve the world's problems and actually able to make agreements to do it. Even countries that really don't get along still all sign the treaty together. And we've had other examples like that. The Montreal Protocol that helped to heal the ozone hole is another example like that. So anyway, it's definitely possible that people in the world can work together to solve problems. And you guys, most of you are engineers, and you're the ones that the society is looking for to carry a big part of that load of proposing good solutions that the society can adopt. I mean, you guys will not be the decision makers about what society actually does, but if you can give people good options, oftentimes they'll take it. And so that's our job. So the part I'm trying to teach you about today is all about how can we make the chemistry models that you would need to understand how a new fuel or how a new engine are going to work. It's definitely just one part of the problem, and many of you study fluid mechanics and other parts of combustion that are really kind of not really focused on chemistry. But as we pointed out, if you have a steady flame, the transport terms have to equal the chemistry terms. So they're about equally important for the overall problem. The chemistry, unfortunately, is super complicated. But fortunately, we have computers, and they can help us to keep track of it. And so really what we need and what the society needs is this kind of black box. So kind of black box so that if people have ideas for new fuels, have ideas for new engines, can put them together and consider different operating conditions of how you might operate it, and automatically come out and predict the performance, predict the emissions, give error bars in the predictions. And having this ability to go from what you're considering to what the outcome would be if you did it is super helpful. And so there's been this big effort, and I see both the CFD developments and a lot of the chemistry developments as part of this common effort to make this computer tool that can help the engineers rapidly assess the options and try to hone in on the best options. and also give good information to the people who are going to make decisions, to the political leaders, to the business leaders, to the investors, and actually to all of society, because everybody's implicated in this, right? Everybody uses fossil fuels. Everybody wants to have transportation. Everybody wants to have heating in their house. They want to have air conditioning. They want to have electricity. And so we're all in it. People in this room and everybody in the whole world is really part of this. And we all want to do it better. And people in this room are some of the people that are going to help to find the better ways to do it. So my career has been mostly trying to figure out how to do the chemistry part of this black box. And as we talked about some of these things before, this key issue is trying to figure out which are the reactions and species that are important. And then a lot of work is trying to get the numbers. And I'll just jump ahead to where we were. So my group has developed a software package called the Reaction Mechanism Generator, or RMG. And you can go to this website and get it. It's not the only tool like this. And as I mentioned, I think as of 1979, 4 different papers came out that all proposed computer tools like this to try to build chemistry models. So that's a long time ago, 1979. I was still in high school. And maybe people might know a guy named Ronzi. Anybody ever hear this guy? Yeah? So he was he was a graduate student then. I guess it was probably his graduate project was to try to write such a thing. In 1979, the computers were not really good enough. People really didn't know what they were doing. So it was like the first try about how to do it. But it was appreciated that it was a really important challenge, and so appreciated that 4 different groups at different universities all tried to solve the problem around the same time. And then over the decades since then, there have been multiple advances, and one line of advance has been the development of the reaction mechanism generator software. And the special thing about this one is that it's open source, everybody can modify it, and it's relatively easy to extend. So you start from the original version, and then you want to change it to the chemistry is more complicated or have a new algorithm or something. It's not that hard to change it. Where some of the earlier attempts, they were written in ways that were challenging for people to modify them. And so although some of the softwares were really good, it was hard to make them better because the way it was coded was not very flexible. And so that was the key innovation of RMG, was to say, from the beginning, we're going to write it in a way that makes it easy for other people to come along and add bits and change things about it. And so I would emphasize this point that it's open source, and you can just go ahead and do whatever you want with this. Now, that might seem intimidating to you, but we have YouTube videos and stuff to teach you about all the parts of the code, and we have training sessions, and there's all kinds of ways you can learn how to do it. It's not really that impossible to do it. The way it works is you put all this information in, just as in my previous picture, and you want to get a kinetic model out. And this thing only makes the chemistry model, so it doesn't do any of the transport stuff. And the key algorithmic point is the idea is it grows models. So you have an existing model that has some species and some reactions, and RMG tries to figure out additional reactions that are possible with those species that would make new products that are not in the model. And then it tries to numerically estimate the rates of each of these reactions. And the default algorithm just picks the one that's the fastest. So the computer computes one of these rates as the highest one, and it says if the fastest one is the most important. So therefore, in this case, like propene formation is computed to be the fastest of all these things on the edge. So propene is then included into the model at the next iteration. And then you just iterate again. And it keeps going on and on until you get bored or you run out of computer budget, and then you stop building the model. So a key part of this is you have to have what reactions are possible. And so far, my students have compiled a list of like 55 different types of reactions. And actually, some other people at other universities have added additional reactions. There's probably more like 100 types of reactions that are in RMG now. And you just have to write down like what bonds break and what bonds are formed in the reaction. And you just write this kind of very formal recipe for what happens in the reaction. And then you also need to provide ways to estimate the rate coefficients in the, say, in the forward direction for the reaction. So how do we get the numbers? Right now, usually people using RMG do a Benson-style group additivity method to estimate the thermochemistry. So they estimate the enthalpy of formation, the entropy, the heat capacities. Cyclic, and especially few cyclic compounds, are a problem because there's too many possible few cyclics, and people haven't studied them all. And so we really don't know the thermochemistry, the ring strain of every different few cyclic in the world. So the ones we do know, we have group contribution methods to estimate them. We also have written some papers about using machine learning methods to try to estimate the thermochemistry of new few cyclic groups that we've never considered or no one's ever studied. And you can also just automatically spawn a quantum chemistry calculation to get the numbers if you figure that we're not sure, we don't know how to estimate them very well. And that might actually be the smartest thing, but of course it's super slow because you have to stop your mechanism construction process and now run a quantum chemistry calculation and wait till it finishes and it comes back and gives you the number and you can keep on going with RMG. And we have the reaction families are defined in some direction, we call the forward direction, and then we always get the reverse rates from the thermochemistry. And so the forward over reverse rate is a thing, it's an equilibrium constant, but it's a different one. It's a concentration-based equilibrium constant. This one has units. The one we talked about before, KEQ, does not have any units because it's the exponential of delta G over RT. These are a little bit different. They differ by the ratio of like a standard concentration. For gas phase, this is how it's defined. It's the standard pressure, which is almost always 1 atmosphere, divided by RT. And then this whole thing is raised to the change in the number of moles in the reaction. So for example, this reaction has delta N equals -1 because you lose 1 mole when you carry out this reaction. And so this gives the formula to how to convert the KEQ from delta G into the Kc you need. For the case where delta N is equal to 0, of course it's just, you don't have this factor because delta N is 0, this term's gone. And then you can just use the regular expression for KQ, which is the delta H minus T delta S, that's the delta G, and divided by RT, and these are for the reaction. And then we need to have the estimator for the forward reaction barrier height, and we also need an estimator for the A factor. These estimates really matter because of the way RMG works. It's deciding which species and reactions belong in the model based on the estimates. So if the estimates are accurate, that's great. If the estimates are inaccurate, not only are you putting in bad numbers in the model, but you're actually including the wrong species and wrong reactions in the model, and you can get really bad results. So the estimators are very important. This is a challenge. So for some families, like H abstractions, where you have a radical attacking and pulling an H off something, we have a lot of examples. So we have more than 2,000 different examples of those kinds of reactions, and we have very detailed estimation rules. And so we can, most reactions you'd ever take in that class, we can categorize them into one of these 2,000 different classifications of H abstractions, and then we have an estimation rule specifically for that class. And those estimates can be really great. So usually for H abstraction, we have quite good estimates. But for other families, like recombinations and disproportionations, our level of knowledge is much lower, and we can't make as many detailed classifications. And so the estimates can be much more erroneous. And so sometimes you can really have a problem. The same with the intramolecular reactions, where like a radical, let's draw a picture. So suppose you have some molecule and suppose you had a radical in this site. So you have 3 H's on here, 2 H's here. Okay, so that's like the radical from a mercaptan. And this radical can abstract, say, that H. So if this thing bends around, so this H gets close enough to that radical site, the H can actually hop. And you'd have the H here and the radical site there. That's an intramolecular H abstraction. There's a lot of them. So if you have a big molecule and you put a radical somewhere, there's lots of other H's in the molecule, and it can grab any of them. They all have different rates because they're like different cyclic transition states. And some of those cyclic transition states have different puckers and different like conformations of them. And so it can be quite confusing. And so RMG has to estimate all of them. But unfortunately, we only know 300 some that we actually know the real numbers for. So we're making the estimates of all the rest of them just from those 300. And so this is similar to the problem we have with a few cyclics, that there's a lot of different possible transition states, and we don't have examples of all the different types. So the numbers might be more erroneous. And this is basically our lack of detail in the estimation rules just reflects our lack of knowledge about these different reactions. Whereas in some classes, people have studied them a lot, like H abstractions. This is bimolecular H abstractions. That's really well studied. This is the example of how accurate things are. So we measure the error by a thing we call Q, which is the root mean squared error of the logarithm, I think log base 10 of K. All right? So like if Q was 1, that means we're on average an error by about one order of magnitude in the estimate of K. And this is all at 1,000 Kelvin. And so if we compare our H abstraction estimates from RMG versus the actual rate coefficients reported in the NIST database, you can see we get Q about 0.8. If we do it by leave one out cross-validation, where we use all of our data to train the model except for one and predict the rest, usually you do a little bit better, but you still have some outliers where you have some oddball reaction types that aren't similar to the rest, and you can't estimate them so well. But either way, we get numbers about the same. So we have errors a little bit less than 1 order of magnitude in the Ks for this reaction family. Compare, if you use the inexpensive quantum method, you probably have errors about the same size as this. So these estimates are actually pretty good. They're about as good as what you would get with a quantum calculation if you didn't try too hard. If you try super hard and do the best quantum calculation you can do, you could get the Qs down smaller. So if you're willing to pay the CPU time that it takes to do a really accurate quantum calculation, then you can get smaller errors than these estimates. So these estimates are like sort of semi-good, but not really great. This is more about how we decide how big to make the model. So we have to decide how accurate do we want it to be. And the way we do it is we decide there's the rate at which we estimate the product E is being formed depends on the estimate of the rate coefficient, the K for this reaction, and also the estimate of the concentration of D. But D is changing with time because it's being formed from A through B to D, and then being destroyed going to C in this model. And so at every different time, you'd have a different amount of D, and therefore you'd have a different rate of formation of E. So we would evaluate the rate of formation of E over all the times that are relevant for our simulation and pick the one that has the highest value and compare it to a tolerance, an error tolerance, times kind of an average rate that's characteristic of the system, of the total loss of stuff across the boundary. And if this thing ever gets to be greater than that error tolerance, then we'd say it's important and we put it in. If none of these reactions are computed to have rates higher than the error tolerance, we'd say we're done. That's sort of how we decide how big do we want to grow the model before we stop. You could, of course, choose different criteria. So, for example, if you're a CFD person, you might say, well, I'm using Fluent. Fluent only can take up to 80 species. So when I get to 80 species, I'm going to stop. And you just keep going until you had 80 species inside the model. And then you say, boom, I'm not going to grow it anymore. But then you wouldn't have any idea how big your error is. If you do it this way, you'll keep growing it until the error satisfies this tolerance. And so that way you're kind of feeling like it's kind of error controlled, but then you might get models that are too large and you couldn't actually use them for CFD. So there's like a lot of trade-offs here. Also, it's not always so clear what to set the value of the error tolerance epsilon. It's like a relative error, but what's exactly epsilon should you use? And that's more or less a thing of experience, but it depends on different systems. Some systems you can use epsilons of a few percent and it's good enough. In other ones, you need epsilons much tighter than that to really converge to get all the phenomena predicted correctly. So this is just how it looks. Let's just do an example in the picture. So this is a case if you had, say, methane and oxygen mixed in carbon dioxide, and you want to see what happens at 1800 Kelvin, 1 atmosphere. So initially, your initial reaction mechanism, you have methane, you have oxygen, you have carbon dioxide. Notice we write O this way with the 2 radicals on it. I don't know if you know, but O2 is actually a triplet molecule. It has 2 unpaired electrons. So it's like a very, very stable, weird radical. So here's the initial conditions, and now the computer's going to compute what can happen. And so all of these different things can happen. You could have methane just thermally fall apart to CH2 and hydrogen, or break a single bond to make methyl plus H. You could have reactions of, say, the CO2 grabbing an H off of methane, so these 2 guys reacting to make methyl plus HCO2. You could have O2 react with methane, grab an H, make HO2 plus methyl. So these are all possible things that could happen. And suppose when you do the analysis, you say, oh, well, it turns out that methyl is the one that's computed to be formed the fastest. So now we're going to put methyl into the model and then keep doing the same thing. And you'll keep adding new species and keep deciding at each stage which one to add. And so this is just the ones that RMG decided were important at this condition. And eventually it stops when it hits the tolerance. It turned out we got up to 112 species. And at that point, it decided to reach the tolerance we had set. And we had 1,904 reactions by the time that happened. So you might not have thought that when you just started with methane, CO2, and oxygen, that you'd end up with more than almost 2,000 reactions happening. But that's what the computer says. So RMG is trying to do an exhaustive calculation of every possible reaction and trying to keep all the ones that are numerically above whatever tolerance you set. And so for the particular tolerance we set this time, it turns out that there's almost 2,000 reactions. Now, if you look at this, sorry, maybe I can draw this, see this. You can see, whoops. Come on. You can see how on the edge, the species outside, you get more on the outside than you have inside. And that's really common, and it gets pretty extreme. So you see in this case, we have 112 species inside the core model that we're going to use as our model, but we actually considered 1,907 species total, so about 1,800 additional species outside here that were things you could make in a single reaction from one of these 112. It's pretty astonishing how rapidly the number of species that you have to consider and the number of reactions you have to consider. So more than 5,000 reactions we had to consider, and we numerically tested them, and of those, 1,904 were found to be numerically significant, and the other 3,000 something were found to be less than the tolerance, and we decided they were negligible. And if you start with a more complicated fuel, the situation gets really out of hand. The number of possible reactions gets really large. So very often we have systems with more than 1 million reactions that we have to consider. Yeah?
Condition, not UKM.
We usually run it at constant temperatures for many different temperatures simultaneously. It's just convenient for the way the algorithm works. You can do it where you have a time-varying temperature, either imposed or just the adiabatic temperature as the thing proceeds. And you can run RMG that way, but then you might run many different simulations starting from slightly different initial temperatures or different initial mixtures, because you want to cover the whole range of conditions you're likely to hit during the simulation. Exactly how to do this, so we normally do this always with zero-dimensional systems because it's way easier. But in reality, a lot of times guys might want to do it for a flame, which is definitely not zero-dimensional. And you can do it with a flame, but it starts getting quite complicated. And recently we tried to do it with the whole CFD simulation, a 3D CFD. And so then you have all these finite volumes in the mesh of the CFD simulation. They each have different temperatures. They each have different compositions. And we want to make sure that we compute all the reactions that are important at any of the finite volumes to make sure we don't miss anything. And then you can see this gets to be a supercomputer problem because you have you might have 1 million mesh points, each different, and you have to do the same kind of analysis I just did here for this 0D case. And they're also communicating with each other because they're transporting properties from one finite volume to the next. And so that gets really quite involved. And I'd say how to do this correctly is still a research question, yeah?
Condition of where to get the transport properties, because there is a big jump.
Yeah, so the question is, do we have a recommendation where you get the transport properties? RMG has its way to estimate the transport properties based on an earlier method invented by Joback, and we use his method. The advantage of it, it's a group contribution method, so we can get numbers for anything. The disadvantage is, who knows if the numbers are accurate? But that's what we have. So those numbers, I think, are known to reproduce the critical properties of pure fluids pretty accurately. So that has some relation to the transport properties. But whether it's really the right thing to do, I think is not clear. There's another smaller community that's very focused on the transport properties. But I would say it's kind of very small. So chemistry community is gigantic. And the transport property community is really tiny. And so you might, if you have a smart idea of what to do in transport properties, there might be a job for you somewhere trying to figure out how to do it better. All right, so that's the general idea of RMG. Maybe this is a good time to stop and ask if there's questions about it, because I'm going to go into even more complicated things. So is this all right? Do you guys feel like you have the general idea of how this works? Yep.
How's the database?
Yeah, that's an excellent question. The question is, how is the database maintained? So from one point of view, it's maintained by the community. It's an open source thing, and you can go in there and edit it however you want. That's kind of dangerous. A general problem in the reaction databases, and I think actually for everything, all data sets, is that there are more than one number for the same reaction in the same molecule. So several different people might have measured a rate coefficient, and some other people calculated it, and none of the numbers are exactly the same. And actually, maybe I'll show you later. Currently, I'm working on this for ammonia combustion. And that's like a case of kind of extreme of this, where you have different mechanisms are published, but if you look carefully at the numbers, they are some of them are completely unrelated. So some people have completely different numbers for some of the reactions and for some of the thermochemistry or some of the intermediates. And so this is a big problem. So in the thermal world, the people have decided that the active thermochemical tables way is the best. So that's where anybody can put their own numbers into the active thermochemical tables. You have to put error bars on your number, which can be a challenge for many people because they really don't know what their error bars are. But anyway, if you put it in with the error bar and you press go on the active thermochemicals table software, it'll try to take from all of the data that it has to get one number that's the most consistent number with the error bar as determined by all the data you have. There's like a Bayesian thing to figure out what's the best. So I think that's the idea of how to do it. In the reaction rate world, the rate coefficients, nobody's ever done it. So we're in kind of a little bit of a mess. And maybe the RMG database is the best we got about this, but it's not that great. So you can put several numbers in, and RMG will try to take those numbers and make some kind of average or estimate that it's going to use. And if you give it the uncertainties, it'll weight them to try to give the one that's the best. But the general problem is that often we don't know the correct weighting because often many papers published with no error bars on their numbers. This is really bad. And so we don't know. And for the quantum calculations also, people often don't really know what the real error bar is. So we have all these numbers with no error bars. and they don't agree with each other, and somehow we have to pick a number, because in the kinetic simulation, you have to have one number for the rate coefficient that you're going to use. And so I think maybe a topic for future discussion is how to alert the community when you find out that there's a big discrepancy between numbers that people are using. Because usually that reveals there's something really fundamentally wrong with at least one of the numbers. And particularly in cases where that's important, where you do a sensitivity analysis and something you care about is sensitive to that number, you really want to have a good number for it. Right now, it's people who are kind of really into the details and the weeds will notice that there's a problem, and they'll know about it, but I think the general community doesn't know. And in particular, it would be good if the funding agencies knew that there was a problem, with this rate coefficient that's really important for something that society cares about, because then maybe they would give some funding for somebody to go measure it, for example. So this is actually maybe a philosophical thing. It's very important to highlight the problems. There's a tendency, for a while there was a big tendency in this community to pretend that everything's fine. We understand it all, it's all great. We have these great predictions. I'll show you some later that work great. It's definitely true. We have some cases where we understand things really well. Ed's in the back, he wrote a very nice textbook. It has some really nice examples. It's really beautiful, it's great. I'm really happy. But we also have some other cases where we don't know what the heck we're doing, and we need a lot more work. And we have to highlight that so that the funders will say, oh man, we better give some more funding to these guys to solve it. And so people will work on the right problems too. Because in my experience with academics, if you don't give them a real problem, they'll make up a fake problem to work on. So it'd be better if you were working on the real problems that really would be important. But if nobody knows what they are, because no one's publicized that we have this problem, we have to work on it, then you can't do it. So you may get this in your own work, is you'll probably, if you're doing experiments, at some point you're probably going to compare your experiment to a model. Or if you're making a model, at some point you're going to try to compare it to an experiment you find from literature. When you compare them, usually they're not really going to agree. Don't hide the problem. Don't only plot the part that agrees. Show the whole thing and discuss, oh, it's great that it agrees in this regime, but it's completely wrong here. Because you highlight where the problem is, that's guiding the next generation of people to work on it about what they should do to fix the problem. If you hide it and seem like everything's hunky-dory and it's all great, then who's going to work on it anymore? They're all going to say, okay, it's all done. We don't need to fund you guys anymore. Let's go work on something else, right? So anyway, I think this is really important. And as a reviewer, if you get to review a paper, same thing. Be critical. Don't let people just go and write like everything's all great. If you notice, figure 3, the fourth point is like way off. You should write back, please, please highlight this, write a comment about it. And not that you want them to erase it to make the plot look better. You want them to actually write a comment so that everybody say, in the abstract, our model is great, it predicts 14 points correctly, but this 15th experiment, if something's completely wrong, we better, that needs more work. And that's actually super helpful to do that. And I try to really fight the theory that all models are supposed to go through the data points. It's completely a bad theory. All right, so now I'm going to talk about even more complexity. Yeah, question?
You mentioned that example that took only 40 minutes.
Yeah, just running RMG using just estimates is like a project of a week or two or something. So it's, if you're an impatient youngster and you want your results fast, it can be frustrating. But on the other hand, compared to the time scale that you might work on a problem, it's not very long. If you need to go back and do quantum chemistry calculations to fix some of the rate coefficients, or you find they're sensitive, that can be longer. So each of those calculations might be at least a couple days to run on a supercomputer. If you have to run 500 of them, like one of my students had to do, it might be 6 months of work to get the 500 to run through. And there's another whole community that's working on trying to make the quantum chemistry faster and easier to automate and stuff for just that reason. And then if you had to go and run them in a 3D CFD, that could be like, you might need to reserve special time on Oak Ridge supercomputer to have enough capacity to even run your CFD simulation, right? So those of you who took Jackie Chen's class, that's what she does, right? So she has to, she's scheduled to do 3 runs a year or something, and she has to get a special grant just to have, I own the computer for 2 weeks in order to run the CFD calculation. So quantum is not as bad as that, but it's still pretty bad. So in my group, we were really lucky. MIT and Lincoln Lab decided to build a supercomputer, and nobody else knew about it. So my group got it pretty much for like 8 months. We were basically the only users. And that was phenomenal. We were able to actually run all these quantum calculations. And now we can't do it anymore because everybody else discovered about the computer, and it's all full. And there's a lot of stories like that kind of stuff. Yeah.
We can input a certain chemical species that we want, but do we have the flexibility to remove, let's say, certain one chemical reaction and then put something else?
Yeah, so you can write at the beginning, you could say, I demand that this reaction must be in my model. And you can also say, I demand that this reaction has this rate coefficient because this is one I really believe. And you can put it in, and it'll override whatever RMG thinks the estimate is.
And then again, we can choose from it.
Yeah, the entirety of it is too big to look at. So instead, it's more like you just pick your reaction that you love, and you put it in. I say, I know that HCO plus O2, I know that's an important reaction in my system, so I demand it must be in the model, and I demand it has to have this rate coefficient because my best friend measured it, and I trust him, and he told me this is the rate coefficient. And I put that number in. So you can do that. And then RMG will add 47 other reactions you've never thought about that it thinks are important, using just its estimated numbers for those. Then you can go back and say, I don't believe you stupid RMG estimates. I'm going to replace it because my buddy also told me that the 14th reaction number is different than what RMG estimated. And you can go and sort of edit that to change it to the number you want. Yeah. All right, so a complication we talked about a little bit before was pressure dependence or fall off, that when you have a reaction and the pressure's too low, you can have the situation where the reactants come together and they bounce back and fall apart, and they don't actually get stabilized to form the product. So when you're observing, like with a laser, you look for HOO, you basically won't see any formed because at low enough pressure, it's just going to all go back. And this same problem happens in cases where you can, more complicated cases. So actually, this is, here's one case. So if you have reactants come together, and they can make a bond, and they make a new product they call C. If you're in the high pressure limit, so if you're doing a condensed phase, like in liquid, or if you're doing a very high pressure and low temperature, you would think that the A plus B would just crawl over this barrier, and then it come down and get stabilized in C. And if I just ran in a GC, a chromatograph, I would see my A and B going away, I'd see my C formed, and I'd be all happy, and everything would be clear. But then when I run it at higher temperatures and lower pressures, the A and B, when they bump into each other, actually already have energies way up here, and they're way above this barrier. So the moment they bump into each other, they're already reacting to go make this C. But the C that's formed is very high energy compared to this stable C. And it's formed with such high energy that it's way, way over the barrier for the second reaction. And so it could go back. That would be like the fall-off case I did here. Or it could also go forwards and form new products, D and E, over this barrier. And if I don't want this to happen, I have to have enough collisions to cool this all the way down so that the C is below the top of this barrier, and then it would be stabilized. So then you can see there's a competition where I need high pressure, particularly when I come in at high temperature, because at high temperature I come in higher and higher. That means I need more collisions to cool it down. And the collisions have to be pretty fast because the K of E scales up very rapidly with energy. And so even I come in a slightly higher energy, that turns out to correspond to a much faster K of E for the second step. So this stuff goes away super fast if I'm high energy. Whereas if I was down here, it still could go away, but the rate would be much slower because the number of quantum states of the transition state is much smaller here than it is up here. This okay? All right, so this process where you put A and B in, you expect to form C, but instead what you observe at high temperatures and low pressures is actually D plus E. And so this is called chemical activation, where we're using the chemical reaction to activate C and make C react. And in this particular case, C, when it reacts, it could go back. So some of it goes back to A and B, but mostly it might go to D plus E because this has a lower barrier. Is this okay? Now, this can be even more complicated because the high energy C often can isomerize. So that means you could rearrange the atoms. It doesn't break any bonds to fall apart, but it just everything moves around. And often there's many isomers that you can form. And so you have many wells here that could all be formed, and you can get all kinds of strange results where the A and B come in, and you can see that the only way they can form a bond will make one isomer of C, but actually what you measure might be a different isomer of C because the C was formed with such high energy it was over the isomerization barriers, as well as being above dissociation barriers. So this is very hard for humans to keep track of because every energy level of C has a different K of E in each direction. And the whole thing, you can solve it with a population balance, what's called the master equation, where you consider all the collisions that can lose energy, and you could have collisions that gain energy from collisions with the bath gas. And so you can put all those collisions in, just moving the energy up and down, as well as all the reactions that's making the flux go to the left or the right. And if you put them all together in it turns out to be one gigantic linear algebra problem to figure out what would actually happen. So we taught RMG to basically automatically construct that master equation for systems, estimating all the rates of the K of E's, estimating the collisional stuff, and then automatically solving. And then people typically want to condense it back down because they don't care about all these energy levels. They just care about the identity. Is it C or not? They don't care if it's C in this energy level or this energy level. It's usually not that interesting to people. So we sum up all of the population of the C states, and we call that the amount of C. We sum up all the constraint of the population of the D plus E states, and we call that D and E. All right? And the rates will depend on the temperature, just like usual. And then additionally, they'll also depend on the pressure. So you get these two-dimensional dependence of the rate coefficient. All right, so can we do this quiz? Can we write down the steady state equation for the population of C star, for say this C star with this particular energy here? What's the steady state equation? We think it should be a quasi-steady state species, right? Because it's a transient species, very highly excited. You guys trying to write it down? So you can tell me. I'll give you a minute, and then we'll try to write the board together. All right, so somebody try to help us write this thing down? So I think we're going to say that it's a steady state. So we say the ddt of the population of C star, it's got to be equal to 0 because it's steady state. So what's that 0 equal to? Speak a little louder.
It's Ka to K1 by Kd into
Okay.
K1 A Ka the
Ka.
forward into the forward
Okay. Times the
K2.
probably it's the concentration of A,
Yeah.
concentration B, and there's anything else in here, Julia?
And then pressure divided by R2.
So I think what there should be in here is a probability of A being in A and D having an energy E. Because it's like not all of the A and B are going to react and make C star. If you look at the top here, only the ones that have exactly the right energy to match. So it's going to be some fraction of all the pairs that bump into each other will actually have the right total energy. So there's going to be some bulk thing here. Is that all right? So this is the formation, right? So that's this arrow at the top here from here to here. So that's the formation of C star from A and B. So now the back direction, see? Okay, so now we have some loss term. And that's like A, D. And now that's going to be basically the population of C star. All right? Yeah? Okay. And is there any other losses?
The one that is going forward to D and E as well.
Okay, so K2.
Yeah.
Okay. Any other losses or gains?
I mean,
Okay.
Pressure.
Pressure. So give me one of them.
It's the probability of PC multiplied by omega. I don't know what symbol we're using.
Okay, so it will be like a loss of due to collisions of PC star. All right, something like that. So this is like the total amount of collisions. Unfortunately, I'm using the same symbol omega. Sorry about that. Here it means collision rate. Yeah, I'll change it to K col. How many effective collisions are there that would take away energy from C star? Are there any other formation, anything else that contribute to forming C star? Julian?
Could D and E react back to C star?
So yeah, so it's definitely possible. You could have plus K minus to something. CD, CE, E, C plus D, something like that. All right?
It's also excitement of the steady, the adopt C back into C star. Going
Yeah,
back.
so there's a whole bunch of
Ionized.
all these other energy states of C star. Each one of them has some probability that on a collision it would get knocked into the energy state C star E. So there's a whole bunch of terms, sum over all the energies E prime, K col, so probability of going from E prime to E times the probability that it's C star of E prime. So I guess I should, these ones are all E. This is E. So these are all the probability that this C has exactly energy E, but there's a bunch of other energy states of C with different energies, and we have to sum over all of them because each of those guys could have a collision that would knock from E prime to E. Is that right? Okay, so this is the master equation, and we have an equation like this for every single energy state of C star. So this is like one of 1,000 equations. We have 1,000 energy states. And so it's pretty messy, but it's linear in P of C star all of the PFCs, these are all just first power. So it just turns out to be linear algebra. So it's a giant linear algebra equation, yeah?
In the solution is still valid to use the equilibrium, the thermodynamic equilibrium to calculate the reverse like KD.
In this case, we're doing it, these Ks are all K of E's. So these are the microcanonical ones that we mentioned yesterday. Okay, Colin, not sure about that. These are KVs. And so we can use the microscopic reversibility we found before. So for example, rho A plus B of E times Ka of E is equal to rho C star of E K D. So if you know how to estimate the densities of states, you can figure out KD from Ka. If you know Ka, you can divide through by this to get KD. And you should do that to ensure microscopic reversibility, and therefore it'll satisfy the law of thermodynamics. And we use the Bayer-Schweinhardt method we talked about yesterday to compute these numbers. But you have to know the vibrational frequencies of C and the modes of inertia of C to be able to do that. All right? Okay, so that's the master equation. That's how you do it. And so the computer just assembles this big equation. And it's just some gigantic linear algebra equation. And it has to estimate all these numbers, all these KVs. So we get those from the R-Kamek equation. But that's coming from the vibrational frequencies and the energies. That's all coming from quantum mechanics calculations. You do quantum chemistry to get the frequencies and the energies. Then you convert them into the rhos and the Ks. And then you can fill out all the entries in here. And then you also need numbers for the collisions and for the probabilities that the collisions would change the energy a certain way. And the collision rates overall are more or less the hard sphere collision rates or the van der Waals collision rates. So those are empirically known. People know what the collision rates are. It's related to the transport property question you asked. This other one about the probability of how much, what the energy changes would be, this one is really not known that well and is kind of complicated. It's like if you have a collision of the bath gas with your molecule, what's the chance that you'll exchange exactly a certain amount of energy? And so you can, like, you know the sum over all of the P's got to be equal to 1. This is a probability. But what the actual distribution is not that well known. There's some people who specialize in trying to measure that. And a guy named Aaron Jasper at Argonne National Lab has figured out how to do the computation to calculate it from first principles, but it's a kind of complicated thing. But it's possible to do it now, so you can actually fill these all in. More commonly, a lot of people say, maybe this is exponential in the amount of energy, something like this. Say, well, there's like a simplistic argument that it should be exponential, the energy difference, the amount of energy exchanged. And the A comes out from the normalization that this is a probability. And so this is another way to estimate the number. And also the upward collisions and downward collisions have a Boltzmann relation, and so you can get some better numbers. So you can rig up some P of E that's not completely unreasonable, but it doesn't mean it's the truth. Yeah.
Is the two questions. Is the A related to temperature? And the other question is, once you did all this, then you need to average on the distribution of energy of A and B, relative energy of A and B, the first probability.
Yeah, you have to do this for sure.
So you need to solve for each one of them and then average.
Yeah. So you have to do this for sure. This one is related to the density of states of A. These are kind of related. So this one we know how to do it. And A and B normally are assumed to be Boltzmann. So it's assumed that before A and B find each other, they have many collisions with the bath gas. So they're already thermal. That's the normal starting assumption. So then this is just a Boltzmann distribution here, so that's easy. what was the second question?
The A in the exponent is
Yes,
related to
this-
temperature, or it's
Yeah,
just an
this
arbitrary
one-
energy cutoff?
Yeah, so for a long time, people would try to infer what that A is by experiments. So they say would measure H plus O2, and they would assume that the collisions followed this exponential rule, and then would figure out what A number you would need to make it so it all worked out to match the experimentally measured HO formation rate. That kind of works,
It's
but
constant or temperature dependent.
yeah, well, normally they would do it at whatever temperature they did it at.
Okay.
Later, then they tried a couple temperatures, and they found there was like some temperature dependence, a little bit. They're not really sure. And so that's like the empirical work from the experiments. Then people like Jasper said, well, let's just calculate it from quantum mechanics. But then he has to run a complicated simulation at each temperature. And he does find that it's temperature dependent. And also, it turns out it's dependent on the angular momentum quantum numbers of the colliding things. And so then you have to do some complicated thing where you consider every possible angular momentum, pairing of angular momentum numbers of the collider and of C, to figure out what's the probability that energy will be transferred. But he did it. So if you're willing to spend a lot of computer time, you can actually calculate all these different collisions and then calculate the probability of how much energy will be transferred. And when he did it, he averaged it all up, it comes pretty close to what the experiments are. So it's probably right. But I would say it's like kind of new, not that well tested. But it was an article in Science when he did the first calculation like that, maybe, I don't know, maybe 4 years ago, something like that. So it's kind of a recent thing that people can calculate this stuff. Before that, for a long time, people would just typically just assume that this is true and then take some A value from some similar system that somebody estimated from experiment without really knowing for sure. It's a super interesting topic, actually, this whole thing of how much energy really is exchanged when things collide. And so there's a lot of work by a guy named Luther. Klaus Luther is an experimentalist. Worked a lot with trying to measure this. And then in this country, Amy Mullen at University of Maryland has made a lot of measurements of exactly how much energy is transferred, but only for specific systems where she could do it with the laser methods. And it's definitely not just exponential, it's a more complicated thing. I mentioned this before, but maybe this might help to emphasize it, that when you have high pressure and low temperature, I call normal chemistry, like this is at, above atmospheric and down at temperatures like 500 Kelvin, 600 Kelvin. What happens is that you're in the pressure independent limit. So at these low temperatures and high pressures, most reactions are just what you'd expect from Boltzmann. So you don't have to worry about any of this master equation stuff. You don't have to worry about fall off. You don't have to worry about chemical activation. It's just going to be normal. So like the atmospheric chemists and a lot of laboratory chemists are working down these low temperatures and relatively high pressures, and they're all fine. However, if you do experiments in the lab with flames, most people work below atmospheric pressure, and flames are always hot, like 1500 Kelvin. And you're in this regime where everything is pressure dependent. There's no Boltzmann. And it's like a total nightmare because you have to worry about the pressure dependence everywhere. Now, in the flames that are important for devices, it's less clear because they're at higher pressure. So if you have a real engine, you might be at 10 bar or something like around here. And so you're still really hot, but your pressure's higher. And so you're more like halfway in between where you're pressure dependent and pressure independent. And so then some of the reactions will be pressure dependent, but many of them will not be, typically. But it depends also on the size of the molecules involved. So the small molecules tend to be more pressure dependent. So for example, the H plus O2, this is like pressure dependent all the time over the whole range that we can actually measure. Remember I mentioned the other day that the guy had measured it all the way up to 950 bar. And he still could just barely see that he was starting to reach the Boltzmann limit at 950 bar, but all the lower pressures, it was completely non-Boltzmann. But if you get a big molecules like a C12, then you can go to pretty high temperature. So an atmosphere can go up to maybe 1200 Kelvin, and it's still all Boltzmann. But if you go to 2000 Kelvin, the atmospheric, it's not Boltzmann at all. It's totally pressure dependent. So this is a headache for the modeling because what's happening in your system depends a lot on what the pressure and temperature is, not just what the numbers are for the rates, but actually going back here, you have like two different products. So at the low temperature, high pressure case, A plus B react and make C. And in the high temperature, low pressure case, A plus B react and make D plus E. And so that's like a headache, right, for the modeler. And also, if you imagine what it looks like for the rate coefficients. So we can find this here. So people often plot things as Arrhenius plots. So logarithm of k versus like 1/2. Okay? And so what we said is like, if I'm doing the A plus B reaction, the one up there, at low temperatures, A plus B is reacting to form C. So I get like normal Arrhenius type behavior, and this is A plus B going to C. But then at some temperature, when it gets high enough, it's going to go like that. Because A plus B is not going to make C anymore. And instead what's going to happen is that from a temperature around here, I have A plus B forming to D plus E. So in this region, this looks like regular Arrhenius. In this region, it looks like regular Arrhenius with a little bit of tunneling, because we're down at low temperature. And in this region, it looks completely screwed up, right? But this is the reality. And so this makes a lot of problems for the modelers. One of them is just a simplistic one, is that how do you represent a shape of a rate constant that does this? It's really pretty weird, right? It's like non-monotonic with temperature. So you need to have like very special representations. And in the modern modeling software, there's a form called Chebyshev, where they basically fit K of TP to a Chebyshev polynomial in 2 dimensions. And it's just like brute force fitting to be able to capture this bizarro non-monotonic behavior. And then this one, it's monotonic, but the slope is like can be completely different, and it's kind of curvy. So again, it's simple Arrhenius is not going to work. So let's stop there and take a break.